This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Jens Gustedt. Jens is a senior scientist at the French National Institute for Computer Science and Control, deputy director of the ICube lab, former co-editor of the ISO C standard, and author of Modern C, all editions. Jens, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
Hello, no, that's great. That's
perfect
about it.
Thank you. So, the goals for the listener today for our show is to understand what's happened in the C world since we last spoke, if you can believe it, 5 years ago now, back in 2020, when your book, second edition, came out. We're going to understand how the latest C standard is going and what to expect if there's anything coming up, to explore the latest changes in your Modern C book and how they apply to the reader, explore your C transition header to help people get set up on C23 if they're not there already, given it's 2025, and you talk about a new comprehensive approach for program failure I'd like to explore if we have time. So let's get started. So what, if you can recall, has happened in the past 5 years in the C world? And bear in mind what happens in other programming languages in 5 years. Has a lot happened to C or not a lot compared to, say, Rust or JavaScript? Or how would you describe what's gone on?
First of all, you have to know that C is really slow. So maybe that's the reason also why we talked 5 years ago and not every year or something like that. So development goes slowly, and we really only standardize things that are already implemented. So there's a long cycle for new features to come in before you even see them. So compared to other languages, for example, which I know the most, C++, they have a lot of more excitement and fuzz and things going on and do things, and then they do them back, and then they do another thing, and then they do something which is not consistent. So we try not to do that. We try to have a steady pace, slow but steady, to go forward. One of the things which were outside of the C standard was another C standard, a technical specification which talks about pointer provenance. So this helps, for those who know what that is, to deal with aliasing of pointers and objects and things like that. And this is work took us 10 years, something like that, and was mainly led by Peter Sewell from the University of Cambridge. So this was a big effort, which now is concentrated in one technical specification, which in some years perhaps might go into the C standard. So this is really one of the things that went on in addition to the C standard itself for the moment.
I'll get that link from you in the show notes.
Yeah. I'll give you a link on that so we can share that. There had been a lot of discussions also about the security of C code compared to other languages. I was not always happy with these kind of discussions because my main impression always has been there have been some major misunderstandings what C is and what C can do and what C wants to do and what other languages make different and what cost-benefit ratio is. C is a relatively specialized language where you can do many, many things. So all security buttons are somehow off, and this is by design, and that's not an accident. So if you don't want that, you probably are programming in the wrong language in some sense.
Did the work on the pointer and object aliases help with the security side of things, or?
On the long run, we hope that this will help, yes. But this has to be integrated in compilers yet, or stated a little bit differently. The compiler vendors really have to check if they are conforming to that model. So basically everybody is convinced that this is the right model, that basically everybody should be there and have that. But there are so many details to check for the compiler producers that they wanted it to be a technical specification, so they already have something written up. but they have to check that over the next years, implement stuff which is perhaps missing and things like that.
Would it be practical to sort of explain an example of these aliases and how they help with security?
The main issue, which is in the title, is provenance. So provenance we define of a pointer is somehow to which object in a wider sense this pointer is pointing. So every allocation, say if you call malloc or calloc or something like that, or if you have a declaration of a variable, gives rise to a different provenance. And if two pointers point to two different such things which were allocated at different times, the compiler can know that they are really different because they come from something very far apart. And this can help by doing aliasing analysis and then being able to optimize, because the compiler can prove that two pointers actually point to different things. So this is basically the idea behind this, and then getting this through all levels of the language and all levels of the compilers and everything. So this is quite technical then in the details.
So this would do away with dangling pointers completely?
This will not do away with dangling pointers by themselves. This will do away with, you have two parameters to the same function, which are pointers, and then the question is whether these can point to the same thing. And so the compiler has to be careful or not, whether when you change one of these things will change the other at the same time.
Okay, that sounds a lot like what Rust enforces with borrow checking and things like that, and sort of garbage collect memory languages might do, where they track every variable.
Yeah, this is related to these kind of questions. In C, you only have these things implicit, and so it's basically a compiler who is then able to prove some things, and this is where things get technically really nasty. So we need a real good model, and there's some real formal specification in the mathematical sense, and that paper was really difficult thing to do.
So we could get in a situation where once you're using an updated compiler, it could find all these bugs for you, because it's tracking everything at that point. So
one thing to notice also in the last 5 years, compilers have been gotten really much, much better than they were 10 years ago or something like that. So they're really able to track things much easier down and to warn you about stuff and things like that. So there has been a real leap forward, I think, in what compilers are capable of. Or at least the compilers I know best, which are these public domain compilers, GCC and Clang. They're
exciting times then.
Yeah, it is. We are in exciting times, yeah.
So our latest standard is C23, and that's what your book's been updated to K4. And can you give us a pitch of what it is, C23?
Yeah, so C23 is the first major addition to C since C11, so 12 years. So you have to have in mind at least the development cycle for C has been. So there has been an intermediate standard which was basically bug fixes in 17. And so C23 is the first which has really new features compared to C11. Among these features are small ones and big ones. There's really a lot. I could point you, for example, one of the things you probably don't even notice is that we reduced the possible sign representations to two's complement. Before there had been other possibilities, and now in C we restrict to two's complement. Everybody uses two's complement anyhow. You learn that in school and everything, but now it's official. Since C23 that this is the only way to represent signs for integers. We changed some spelling of keywords. We added constx facility. We added auto and typeof for type inference. We added attributes, which gives you the possibility to annotate constructs in the language in a systematic way.
Yeah, we'll be going over some of those shortly in the next section.
Yeah, we updated the Unicode support. So identifiers in C now are really ruled by Unicode, what's possible to have in an identifier. There are clear Unicode rules for that. And before we had some homebrew tables of what was possible and what not. And so we changed to be conforming to this other standard. We also added more facilities to the standard C library to transform different encodings. We add bit fitting utilities. Everybody probably knows how to do a pop count so counting the bits of an integer. And everybody probably does it wrong if they only have half an hour to program this. So this gives you a unique way to do that with a function call, and which is then optimized by your implementer for your platform, what you have. We have checked integer arithmetic, so you can check for overflow. And we have added const safety for some library functions. So it's just rough, very rough overview.
Thank you. We'll dig in a bit more in the next section. So how does that work? Say you've just explained there's a new function to help count the bits in an integer.
Yeah.
So practically wise, that would appear in glibc.
Practically wise, this appears, or let's state it different. All the compilers already have it with different names. And so we are just putting some glue on top of it, which is a unique name. And glibc then would provide that in a header too. So you can...
So you'd get an updated version of GCC, which would come with the headers.
Yeah, so you can use that portably for different...
And that function is then defined in the GCC source code? Someone's written it?
Yes, for most of these functions, actually, they exist, for example, in GCC, they exist as built-ins. So this will not even give rise to a function call at the end. This will be directly transformed into some assembly by the compiler. This is already built in with this prefix __ built in something behind. GCC has a lot of them. And what the header of glibc then only would give you basically a macro interface, which translates to this built-in of the compiler.
And the GCC team would have done all the work inside.
Yeah, GCC team had done most of the work already before.
And then to validate that, they'd look up the C spec and make sure the inputs and outputs match what the spec says.
Yeah, exactly. So this is the bit of work they have to do. Because when you standardize things like that, everybody has chosen a different name for these kind of functions. And so we have to agree upon one name for a specific function. And then everybody has to do some homework, getting things right with exactly the right name and right order of parameters and things like that.
The stakeholders and all the different compilers would be represented in the C committee. Is that how?
Not all, but some of them, yeah.
Some of them, yeah. And probably not for this function, but for other functions, would the internal implementation of these functions will obviously be different depending on what team has put them into GCC or CLang or wherever?
Yes. Even for these functions, these could be different because they might depend a lot on the processor that you have. So the processor an Intel versus an ARM may have different primitives. And so the goal for the compiler team would be to match that to the good primitive, which makes this quick and easy. And so there are certainly different choices to make for the implementation for certain things. And what's only guaranteed by the standard is the semantics of such a call. So
yeah,
basically that it does the same thing.
Or would there be situations where your project or program would be faster compiling it? Not compile speed, but actually runtime might be faster if it's built with GCC or CLang because of those internal implementations?
Yes, sure. There are always differences in these things between the different compilers.
And that's something that you have to figure out, I suppose, when you do benchmarking.
Yeah, if you do benchmarking, you can figure this out.
It's nice to think about how it goes from standard to implementation and actually getting in your hands and how that could be different as well. And if you're on the GC team or just a C programmer in general, how do you recommend people keep up to date with not only what's just in the standard, but do they just publish the standard and we're all left to go and read it? Or is there another source of information that you can say these things would benefit you? Or does it just trickle downstream until your compiler says something?
No, it's really a process of compiler people adding things to their compilers, and because they have a demand. So usually when there's new feature, there are people that like to have that. then compiler vendors implement this. And if a feature appears in several compilers and the community says, oh, yeah, this one is now something that we think that is stable, then we're going to standardize that. So this is really a feedback loop in that sense.
Okay, so it's back to front.
The standardization often then is only, giving a unique name to that function or something like that.
That makes sense, because you're not just going to make up stuff in a standard just because you wanted something to do. It's because you're trying to
tendencies to do so also for certain things. But for all what I said, at least for the C library, this is usually really the case, that this comes from somewhere and is then standardized.
Okay, thank you. So is there going to be such a thing as C26, or is it going to be C34, or how do you think that will pan out?
Yeah, so there will be no C26.
Okay.
We are working on C2Y, so C26 would not exist. C2Y, where Y is not yet fixed, is in the works. So there are already a lot of papers accepted for that. There's an intermediate version of the standard where the editor has already integrated most of these changes. But this will certainly take us at least 2 or 3 years still. So this might be 28, 29, something like that.
That's pretty good, though, because the last one, C23, that's another 6 years.
Yeah, so 6 years would be our usual schedule, let's say like that, by experience. But this time, this will not be just a bug fix release. This time, this will be a real feature release also.
Okay. The one before was C11, so it's quite fast.
There was C17 in between, which was this bug fix release. So.
Okay, yeah. And is there any major, you said there's new features in C2Y?
Yeah, there are some new features, which, for example, one thing we get from C++, actually, this is the definition of variables inside if and switch statements. I don't know if you know about that feature. In the expression part of an if, in C++, you can first declare a variable and then evaluate that variable. For example, if you're making a system call, you can assign the result of the system call to a temporary variable for which only lives inside the if statement and then check for the value of that.
Yeah, recently I've been doing mainly Rust programming, and that's something you do in Rust quite often.
Yeah. So this kind of neat feature, which is not very difficult to implement. We have added things to the preprocessor. For example, we now have the counter feature. So you have the __ counter __, which gives you at each time which it's evaluated in the preprocessor a new number. So you can do that for saying uniquely naming some variables which are produced by macros or something like that. We have removed imaginary types. So before there was a concept of imaginary type, which nobody implemented.
Was this one of the things that appeared in the spec first and then didn't appear?
Yeah. So there was at one point in history, there was one implementation for that. But the way complex numbers were described were basically described as being reals and then plus this imaginary part, and how this imaginary part, which is then imaginary in both sense of the terms, would look like. And this complicated the write-up of the standard a lot and made it really difficult to read at some points. And so we decided that we get rid of that and removed all that from the standard and have just complex numbers. We have added complex literals, which didn't exist surprisingly before. So now if you just have a real number with the suffix I, then you get a complex with this number as imaginary part. Things like that. And there are a lot of things which are already voted in favor, but still need adjustment before they can really be included. And so there's still a long way to go for this. There we have a real large backlog of papers, which we can only treat so much in a session that when we're meeting. And so
the only thing I remember about imaginary numbers is at university with engineering, just I and J. used to represent.
Yeah.
Maths. Yeah, so these things that are getting changed, what's the process for that? You said they publish a paper, you review it as a board, and then you chat about it, or I think we might have spoken about this last time we spoke, but in the next 2 years or C28 or 29, what goes on in those years?
Yeah, so as I said, basically, for example, like this counter preprocessor feature, this is basically already implemented in every compiler. So this exists. So you have to write a paper to already first advertise that, why you want that, and then you have to provide text how this would be integrated into the standard. And then this goes usually over some iterations with the committee. There's discussion on the email list, and then there's discussion.
So is this like a working group type thing, the mailing list?
There are working groups, but most of the things are done in C are done in plenary. We are only about 30 people or so which meet regularly.
So somebody writes a paper and publishes it to that list for you all to consider?
Yeah.
I see. Okay, I was just trying to figure out where people find those papers. But it's all a proper process.
There's a website for the C committee where you can find all these papers.
Okay, I'll get that off you later.
Yeah, we can put that in the links too. And you can see all revisions of all papers. And it's really long list.
Okay, I think we've covered our introduction, a bit more than that. So we might speed through the next section. So I've called this section the latest C standard, bracket C23, and upcoming changes. So I think we've touched the upcoming changes quite a lot with C2Y, which sounds really cool.
Yes.
But let's pull apart some of the things we just mentioned. So I've got a few bullet points here that I'll take you through. Questions. So why are these improvements to integers and enums needed that are in C23? And I've got a quote here where you say, in the updated version of your book, Intro, or the marketing pitch for it, I think, there are new bit precise types coined _bit int, brackets capital N, new C library headers, standard stdckdint.h for arithmetic overflow checks, standard bit.h for bit manipulation, possibilities for 128-bit types of modern architectures, etc. So immediately I thought, integers are integers, what's changed and why are these things needed? So could you give me some insight into those?
First of all, integers are not integers. There are 15 different integer types, standard different integer types, and you have a lot of problems with overflow, with conversion. So if the conversion is narrowing or widening and things like that. So because we don't have a big int type as other languages have, you always are reduced to something, some given precision. Whatever that precision is, what you choose, you really need to be aware of that. If you're going too far to big numbers, then you have wraparound or something like that, or stuff like that. You have the problem of if you are doing, for example, comparison between two integers, when one of these integers is signed and the other is unsigned, what should be the semantics of this comparison be, and so on. So this is not completely trivial in C, how to deal with these. And therefore, we talked already a little bit of this bit manipulation thing. So this offers new opportunities, new interfaces.
So that would be the standard bit.h header.
Yeah, this is this stdbit.h thing. Standard checked integer gives you an interface where you can check for overflow. So you do arithmetic, say an addition between two integers, and these functions which are in this interface, in this header, they will not only give you the result of that addition, but they will also give you a flag back whether or not you had an overflow in that addition or not. So you can do checks, you can abort your program if your numbers are getting too large or whatever you want to do when this goes down the drain.
So up until this was standardized, people would be doing this anyway, but just have created something themselves.
Yeah, well, again, there were built-ins for compilers which did that. So this was not portable, not so easily portable, or people did their checks by themselves and then with all the possibilities of getting this wrong. So if you have time and look up on Stack Overflow, for example, there are questions of how to do that, you have a lot of answers and a lot of them are wrong. So you have some special cases which are not covered. And the idea here really is to have that done on one hand correctly, which is already a good thing. And then also using, as for the bit manipulation part, using already the right assembly instruction, for example, for that. Because most processors already do that correctly. They have this overflow bit, and you just have to do the addition in the assembler and then read the overflow bit whether or not this worked or didn't work. So this is much more efficient and much safer. So this is basically the idea behind. The other thing, which you also mentioned, is this thing with 128-bit types. The problem has been that we had an actually upper limit in the width of integers, which is the type uint max _ t, which on most modern architectures was 64-bit. And on the other hand, in there are really applications where you really like to have wider types, for example, for cryptography or checksum calculations or things like that. And the modern processors all implement these 128-bit arithmetic, but there was no way to map them correctly into the C library, in the C language, because we had this artificial restriction on how wide an integer could be. So this was a lot of work of fiddling with the standard text actually to allow that to happen, and now to offer the possibility to go beyond these limits that we have.
And does the term wide integer, is wide the bit size?
Yeah, wide is the bit size,
Yeah. And do you get input from, going back to the standard, from CPU companies that say we now support this, we should put something in the standard, or did they release a tool set with the CPUs?
Yes and no. We have one big player which is really invested also in the C standard, which is Intel, but they are mainly invested because of their compilers. So they are really supporting Clang and they are really interested in C from that perspective. We had this _bit int (n) types, which actually also came from Intel, but for a very different reason than one might think. They had this because they wanted to have such a type in FPGAs and things like that, where you really want to be able to design your integer type with every bits such that you can lay out your network of computing correctly in this FPGA with exactly the resources that you
Was that an FGPA? I haven't heard that word since university.
Right.
And I think it's field programmable gate arrays I was thinking of,
Yeah.
but that's not what you said.
Yeah, but that's what I meant. So,
Oh, okay. FPGAs, yeah. I remember doing that in my degree. Do you think these wider types, are they getting driven by machine learning type stuff, AI type stuff, or where's the need for them coming from?
Machine learning goes actually in the inverse direction, which is not yet covered by the C standard. The machine learning guy, they want to have floating point, which is really short. So for them, float, for example, with this 32 bits is already much too large. They want to have floating points sometimes with 8 bits only or something, because they really want to do approximate computations very, very fast and with really slow memory footprint for everything, etc., to do more and more. And then they only need to do some steps for the real precision afterwards. So they really have that, and they're currently, and this is one of the main reasons we haven't standardized that, I think for 8-bit floating point, there are at least 10 different specifications by different providers, which are all different in some aspect somewhere, and what the mantissa is, or they present things. So this is probably something we will see at some point to be standardized, but there's still a long way to go, because everybody now has their own 8-bit floating point somewhere implemented. and it's not compatible to what the other guys are doing. And so it's not easy to standardize.
No, it's interesting. I thought maybe it was like the vectors and things they use and just to speed everything up.
No, it's more the crypto guys, things like that. So it's really interesting for crypto to at least to have bit operations on large vectors. And this works quite well for them.
Excellent. Okay. So I'll take us through a couple of more bullet points, but we've still got a bit to cover because I want to talk about additions to your book. So we might move a bit quicker through these ones. So what is a null pointer constant in regards to the standard?
Yeah, so before we had null all in capitals, which is just a macro which was somehow ill-designed or not well specified. So this can, underneath the hood, can be different things. And this led to potential problems, for example, when you use that as an argument to printf or something like that. So we had this sitting there. We cannot easily change things like that because it's used by everybody. And so we invented something new, which hasn't this ambiguity which null, all capital null has. So we integrate that really into the language and not into the macro preprocessor.
All caps null macro. Has that remained the same since C was first created 50 years ago or so?
Yeah, basically. So
all of a sudden in the 20s, they decided, no, we need something else. It's never come up before.
It has come up before. So C++ had, so this null pointer comes from C++. C++ has done this 12 years ago, at least, I think in C++ 11, I don't remember exactly, because they had exactly the same problem, because they inherited that from us and they invented that. And so we just applied that same change to C.
Cool. And what are syntactic annotations with attributes?
So perhaps people know this underscore attribute feature from GCC, and Clang also implements that, where you can add properties to a function, to a parameter, to a variable. You can basically, there are a lot of attributes like that which were implemented before. The problem with the approach that they had was that this was syntactically not clear to which construct an attribute applies. So sometimes you put the attribute in front of the function declaration or behind the function declaration, and these different places had different meanings, and it was something, which engineers do. So somebody invented something here and somebody there, and then you had a lot of add up of these kind of features. And the attributes, which is also a C++ feature, which we adapted to C, is now a syntax annotation where it's unique to which construct an attribute applies. Basically, big rule is just as for other things, it always applies to the left. So if you put an attribute, for example, behind after a function declaration, after the closing parenthesis, and this would apply to the function, to the type of the function. If you would put it after the identifier, it would only apply to this specific identifier and things like that. So you can annotate things like that. There are some standard attributes. For example, something like deprecated, you can mark an identifier as being deprecated. And so compiler will tell the user who uses that at every compilation, hey, guy, don't remember this one you should use. And then there are a lot of vendor-specific attributes where compiler vendors have the possibility to invent everything, stuff they need, they want to add to their compilers for flow analysis or for whatever feature they want to have. But it's clear by the syntax to which structure of the program this applies.
I've got 4 bullet points coming up. I'm going to just say them all out loud, and then you can pick 2 of your favorites because we need to move on, I think, to talk about your book.
Okay.
So the first of the 4 is, what is generic programming with regards to type inference? with auto and typeof? What is default initialization with curly brackets? What are compound expressions with lambdas? And what is so-called internationalization? So which of those two get you excited the most that you'd like to talk about?
I won't talk about compound expressions lambdas because they're not even in the standard yet. And I won't talk about internationalization because we already talked about Unicode and things like that a little bit. So let's talk about generic programming, auto and typeof, and also initialization with brackets, which are both or all three. Auto and the brackets are features we also inherited from C++. So auto is a possibility to keep your code consistent. If you have a function which depends on a parameter x and this has some type and you don't remember that type, but you need another variable, auxiliary variable somewhere, which depends on that and which should have the same type, you just type auto y equals x, and then y gets exactly the same type and value as x, and then you could continue.
Yeah, it's kind of like a dynamic language then, isn't it?
This just helps you to stay consistent. So if anybody changes x during development, then y will change automatically with it. And typeof is a little bit more complicated. It takes an expression or a type as an argument and then derives the type from that. This is used or useful in a lot of macro development or things like that, where you like to be able to deduce types or automatically from what you get as macro arguments, for example. Before initialization with braces closes, say, a loop or whatever. Before initialization in C, you always had to put at least one initializer into these braces. So you had to say, if you have an array A of type double of size 5, you would have to put at least 1 0 into these braces for initialization. And the rest would then be before initialized. And now you can just omit everything and just put the braces. And by that saying that every member of your array is before initialized. And this even works for these so-called VLA, variable length arrays. So even for arrays where you don't know the lengths, where it's determined not at compile time, but at runtime, you can do that. So the compiler will produce code that does this initialization for you. You don't have to do a for loop to initialize all your array, which you had to do before.
So it saves the programmer some time.
Yeah, and ensure that it's consistent. That's always these two aspects, actually, that you really have to be sure that people don't do too much errors. So
with these types of things, if you switch to using them, would you feel confident in using them, or would you need to create some tests to make sure they're doing what they should be? Or how would you advise people to get rid of code, basically delete stuff because it's now done automatically somewhere?
So first of all, again, with these braces, compilers implemented that since a long time.
Okay.
Because C++ also has that. So it's already there in the compilers. It works. People use it. And now this gives you the official stamp that this is how it's supposed to be. And you can change all your code to that without any difficulties. So even if you have to backport it to some little bit older version of your compilers, this should work.
Excellent. And you said compound expressions and lambdas aren't really standardized yet?
Yeah. Unfortunately. I put a lot of work in lambdas and it was not taken for C23. I'm not sure that we get something like that for C to Y. I'm not sure. People are very divided on that, and then it's really difficult to make progress.
What's the use case for it in C?
The use case for?
The lambdas and compound expressions in C. Why do you want it?
Yeah, lambdas, they exist in many languages. So, for example, in C++, a very useful tool if you have callbacks which you want to pass into a function. And in C, now the official way is always to create outside of the function you are currently writing. Before, you have to write this callback, as a separate function far away from where you're going to use it. And then you pass a function pointer to that function as a callback somewhere else in your code. So you get these things very far apart, and that makes it difficult to maintain and everything. So lambda would be some sort of short function which you could actually put in place where you pass it as a callback. And so everybody would see immediately at that place, here I'm doing callback for, I don't know what, press button or whatever. And you see how that works and where that is all in one place.
I suppose a lot of arguments against these types of things is that your IDE will help you find things.
Yeah, this is part of the argument. Then there's part of more or less small design questions on how to do that semantically, syntactically. The question is, if you have a lambda in a certain place, what does this lambda see from the surroundings? Is it possible to access local variables, for example, in the surroundings or not? Or what would be the mechanism to integrate them? And there people, it's a little bit exaggerated, but sometimes you think people would kill each other for these things.
Well, people are very passionate about what they love.
Yeah, stated like that. They are very passionate about things. Yeah.
That's the nice way to say it. I suppose we should talk about the bit that you're most excited about, and that's your book.
Yeah.
Modern C 3rd edition. I can't believe it. I've actually got the hard copy posted to me a month or two ago when it came out.
Okay.
So I was very excited to receive that. So yeah, let's do the chat about that now. So given what we've just spoken about, and we went quite deep and some new things that I wasn't expecting to talk about, which was great. What does the latest edition of your book bring to the C world?
So it has been completely reworked for C23. So integrate all the shiny new features from C23. If you scan, so it's difficult on the hard copy, so you would have to go to the electronic copy. If you search for mention of the string C23 in it, you get about 200 mentions. So this is all over the place. And if you really want to know what C23 is, that's a really good way to do. You see it every here and there. There is this little thing which makes things easier, where you don't have to think about that, where you can do things easier with another feature, etc., etc. So in that sense, it's really deeply integrated now into the book. That really was also the motivation to do that.
It's also really good that the standards are quite far apart in time. So you get to update a book to the latest standard. Yeah. It's not like every couple of years. So
Yeah, that's right. So the process of generating this new edition was also quite lengthy. So, which I did in some parts in parallel to what we did on the standard. Still, it took a lot of time to actually appear at the end. So,
how many pages did you add?
Oh, I don't know. There's some.
I'll work it out. I've got both copies here.
Yeah.
I'm a bit of a fanboy.
So it's thicker. It's thicker, that's for sure. But I didn't do page counting.
You talk about one of the pictures in your book that you've got an easy transition header to get across to C23.
Yeah.
Can you take us through that a little bit?
As I said previously, many of the features already are there in compilers. Only often this is written, this has a little bit different name, or perhaps maybe even arguments are in different order or things like that. So what this header does, which you can download with the examples from the book, is to provide you already the interfaces that match that on your current, perhaps not so updated compiler. I only tested that for GCC and Clang, so I wouldn't know how this really works for other compilers. But let's say that these are probably the major compilers nowadays. So to give you an example, there is a macro in C23 which is called unreachable, and GCC and Clang already have macros built in unreachable. And so what my header does is just matches this new wording, new name to the old ones. So this is a little bit the way this works. I'm not sure that you even would need that nowadays. So I've written that, 2 years ago or something. Now these compilers have officially transitioned to C23 already with their newest version. So probably you won't even need that. But if you still are stuck with a Clang from 2 years ago or 3 years ago or something like that, you could use that.
Yeah, in the C world, it's not unheard of, is it?
This is not unheard of, exactly. But you can use that and you can be sure that you're future-proof for future changes once.
Do you know how many versions of C standard the compilers keep around in their own source code? You know, if you mark your code C11 or C89, it's still C89. But
GCC still has all versions of C.
Wow, that's amazing, isn't it?
It is, and it's a lot of work to keep that consistent. So, yeah.
Wow. Cool. So another thing that was really exciting in your book was what you've called a comprehensive approach for program failure. That really piqued my interest. Can you take us through that, if it's possible?
That's nice to hear, because I put a lot of brain effort into that. And one of the reasons I started writing this up was because I had the impression that there were a lot of misconceptions about what failure is in C or what a fault is in C and things like that. So basically, I was categorizing program failures into 4 main groups. The first one is wrongdoings. So it's your fault when you do something wrong. I don't know, you reference a null pointer or you do whatever bad thing you can do in C. This is basically the easy part where you should, whenever it's possible, get a diagnostic from your compiler, or your program should really fault very quickly or something like that. Then there is the next layer of faults that lead to program failure, which are program state degradation. So, for example, if you have storage exhaustion. So this is generally something which you can check if you check, for example, the return of system calls. So if malloc really gives you a null back, then you know there's something deeply went wrong with your program. There's no storage available anymore, and so you really should stop and do an emergency exit from your program or something like that. So that was a second level. The third level are unfortunate incidents. Unfortunate incidents are things that you don't really notice, which are difficult to track and things like that. For example, like a race condition in between 2 threads in a threaded program. There are 2 entities doing their things and 2 threads, for example, and seen locally, everybody's doing the right thing, but together they don't work. This is something which you can basically only avoid by really careful design. So this false program failures for unfortunate incidents usually only appear when you have a bad design. But what is a good and what a bad design obviously is a really difficult question. And then you have the fourth thing, which is a series of unfortunate incidents where you are basically caught in a bubble. You have doing decisions on your own. You're going around a block in a city, for example. At each corner, you decide because of something to go to the left. And if you do that consistently, you will always walk around the block and never get out. So you're caught in some sort of bubble because you're taking local decisions which don't have you make progress at some point. So this is also a really difficult design question to answer. So this is what failure is, but the problem then is that you have to really distinguish the error. So if you talk about a sickness or something like that, so this would be something which is wrong or goes wrong from the way it manifests from the symptoms. And this is something which is often conflated by people in C and generally in programming languages, I think. So symptoms can be compiler diagnostics, they can be compilation failure, there can be program termination. or even worse, there can be real crashes, there can be erratic behavior, silent misfunctioning. All these different symptoms can appear if you have a failing program. You really have to navigate these to know why your program failed and what to do against it to, first of all, try to do something to work that it never happens, or if you can't avoid it, then see how to manage if it occurs and terminate your program, for example, in a controlled way.
Okay, just to summarize those 4 categories you created, you got what you call user errors.
Yeah, wrongdoings, I call them, yeah.
Yeah. Memory system issues.
Yeah, state degradation. So memory system issues, but this can be, I don't know, file system full or things like that. So.
And then 3 would be unexpected events.
Yeah.
And 4 would be a combo series of those.
Yeah, a combo series of those which make you seem to doing progress, but actually you don't.
Yeah, that could be something like you see in the news when AWS goes down or something, and something triggers something else, and it's not supposed to spike that much, and then that doesn't feed back to that, and it keeps going and keeps going, that type of issue.
Yeah.
Okay. How do we approach these 4 things then?
So the first is discipline for wrongdoings. Have a programming style. Always keep to that programming style. Listen to your compiler. If they're telling you here's something fishy, there's probably something fishy, and so you should do that. What the compiler suggests, generally. You should, against program state energy generation, you always should check return of system calls. So every system call should either be in an if statement, or you should take the return value into a variable and then decide whether or not this was successful.
Does the standard or compiler help with that type of thing?
Yeah, so usually the C library, for example, you have for all calls, you have return, and you have specified what happens when an error occurs. And so you can program against that. So
no, but does the compiler enforce that you check those?
There are possibilities that compilers enforce to check these, yeah.
Okay, cool.
This is possible. So these are the first 2 in that sense. This depends on the quality of your code directly, how you write it, and that you follow a style which is consistent in itself, and you have the right tools, compilers or analyzers or something which give you hints on what to do. The other 2 are much more difficult to handle. So they really need careful algorithms design. So, for example, race conditions between threads, you really have to look and learn into, and there's a chapter in the book about threads and atomics and mutexes and all that stuff, how you can avoid that race conditions occur in the first place, for example. For this force, for these unfortunate incidents, it's much, much more difficult because you have basically to have proofs on your algorithms that there is always progress. And this is not something which is in general, or whether general rules or something how to do that. You really have to do some thinking too.
And you could probably apply those 4 rules that you've created to any language, really, any programming.
I guess so, yeah. Probably you could have that for different languages, where you certainly have different kind, and this is probably something which you could somehow rank languages, whether or not the first 2 points are detected automatically, or basically the syntax inhibits that you're doing certain types of faults or something. So their C is probably on the lower end. So you can probably, and we're trying to do that at some point, improve C and the diagnostic that are given. For the last 2, there's basically all languages have these problems, and basically all languages have the same amount of detail or whatever, which they can help you or don't.
How do you yourself, when you're creating this approach, say for the thing with threads example, do you have a set of example programs that you write to prove these things or work around them? Or how do you translate this sort of real world experience you've gained into your writing?
For all threading, for example, and problems like this, I think the C standard gives the right tools with atomics and mutexes and things like that. So you really only have to apply them consequently and consistently to get things right.
I was just thinking maybe you have your own C project that you break things and fix things and break things just to have a play and compare.
Yeah, so what I'm currently working on is having contracts for C, which is something like that to make some guarantees about things automatically, which is, I already published a paper for that, but which hasn't yet even been discussed by the C committee. But this would be a way to go forward, to have actually more tools in the language and the syntax to guarantee certain things and have more or less automatic proofs for certain things. So this would be one direction to go, but this is early stage, I'd say.
Well, I think that's probably time up for us. Is there anything in your book that we've missed that you're really proud of, or even not in the new edition that you want to highlight that you think will make people's lives much better in the C world?
No, I think we covered it well. There's so many things in the book, so you really have to dig through it to learn it.
So obviously the C programming language and standards and world is powering on. But if there was one thing a software engineer should remember from our show, what would you like that to be?
I think the most important thing is to stick to some sort of coding style or something like that. Be consistent. That's really the most important thing. And listen to your compiler.
That would solve 50% of your 4.
Yeah. So basically compile things without warnings and then you're already quite good. So
yeah, because they're there for a reason. So pay attention.
Yeah.
Do you think the C standard helps any other programming languages?
Yes, a lot, basically. C is not only a programming language. C is also somehow a lingua franca, how to talk between different languages. So basically all languages that you see today, at some level, they interface to C, and then some of the work is done in C.
Yeah, that's what I think about. Like I was saying, I'm doing a lot of Rust work at the moment, and I'm seeing more and more libraries be written in Rust, and then they expose a C interface. Yeah. And every other language then uses that interface to use that language.
And often it goes the other way around. So, for example, for Python, once you want to do things efficiently and fast, people create some C library which they interface from Python. So
yeah, and then that means everyone else can get it because it's written in C.
Yeah, it's written in C and then easy to use in Python. So these are these compromises which are done today.
Should someone learn C today that's never programmed before?
Yes, sure, certainly. It's really one of the programming languages it's always among the first, second, or third used programming languages in the world. So
I suppose for me, I kind of think of it like learning to speak English. Everything speaks C. You'll get by if you can translate ideas and things from C, and you can always understand what's under the hood if you can.
Yeah.
I don't know where you hang out. Can people follow you somewhere, or how can they get in touch if they've got some questions?
I'm on Mastodon, so you would easily find me there. Yeah, also LinkedIn, but I'm not very active. So basically it's Mastodon nowadays. I tried not to go on too much on these commercial platforms.
Thank you for coming on the show. It's just as much fun as 5 years ago, more so. So thanks for coming back. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.